Have you ever heard of blue energy? Some experts believe it could power half of Europe, while others say it could generate as much electricity as 2,000 nuclear power plants. And all of this in a sustainable way, completely independent of wind and weather. We are talking about electricity generated by osmosis. When fresh and salt water mix, energy is actually generated. With a new pilot plant, it should be possible to supply a city like Barcelona or Marseille. And a research group has now even managed to double the energy yield compared to the commercial standard using a new approach. How this technology works, how they managed to double the energy output, and why electricity generated by osmosis has a good chance of becoming a reliable power source of the future. All of this we're going to talk about today, and with that, welcome to the German Science Guy. I'm Dr. Jakob Beautemps, and in Germany we say Los geht's! There are some osmosis power plants running already, for example in Norway, but also a few other pilot projects. In general, there's a lot happening in this field right now. Theoretical calculations estimate the oceans alone contain up to 2.6 terawatts of osmotic energy. The International Renewable Energy Agency says, technically speaking, we could harness about 647 gigawatts of this energy. That alone is enough to supply the United States, Germany, France, Italy, and the United Kingdom with electricity. But there's a catch. So far, we haven't found the right technology to harness the potential. But as I said, things are moving fast with new findings from research and a startup from France that claims to have even solved the biggest problem. So let's take a closer look at that. But first, what is the basic idea behind the osmosis power plant? It taps into the unique properties of the end of rivers where they flow into the sea. That's where the fresh water flows into salt water. In salt water, ions, that are charged particles, are much more concentrated. And it's precisely this imbalance that can be used to generate electricity. Normally, when salt water and fresh water meet, this difference is balanced out by the force of diffusion. If we now place a barrier between the two liquids, things get interesting, because that brings us to osmosis. This barrier is a semi-permeable membrane. However, this membrane is only permeable to water, so the ions from the salt water cannot flow into the fresh water to balance the concentration gradient. This results in osmotic pressure, a sort of suction created by the ions in the salt water, which draw water from the fresh water to dilute themselves. But how can we use this to generate electricity? Well, the first experiments on this were conducted as early as the 1950s. One of the first and most promising methods is reverse electrodialysis, or more specifically, nanofluidic reverse electrodialysis. The ion selectivity of the membrane creates a charge difference between the two fluids, and this can now be harnessed. To do so, there are cathodes and anodes in the solution. The incoming ions react at these in a redox reaction. This allows electricity to be generated in the end. However, the efficiency of this process depends heavily on the membrane. It must meet certain criteria. The first one is high ion selectivity, meaning certain ions pass through particularly well while others don't. The second one is low electrical resistance, followed by high mechanical and chemical stability, and of course a long service life. In the case of nanofluidic reverse electrodialysis, 2D nanofluids are used for this purpose. These are particularly thin membranes that often have high selectivity and also last a long time. However, truly good solutions have not been found for a long time. There was always a problem. To achieve a high ion flux, a membrane with very low resistance is needed. But very often, this reduces mechanical stability and also shortens the service life. Achieving both seems to be very complicated, but that could change soon. A research group has now achieved some pretty promising results. Before we take a look at them, please subscribe to the channel so you don't miss any more science videos. Okay, in the new experiment, a membrane was tested that does not suffer from any of these problems. Despite its very low resistance, it exhibits quite high mechanical stability. Commercially available membranes currently have a power density of about 5 watts per square meter. In this experiment, they simply doubled that to 10 watts per square meter. To achieve this, the research group produced a membrane made of polyaniline and cellulose gel. The exciting thing, however, is that the materials themselves weren't actually the key to the success. In fact, the increase in performance has more to do with the membrane structure. Different materials are usually simply mixed together so that they are evenly distributed. If we take a closer look at the materials, we notice that this isn't ideal. This is because the negatively charged cellulose gel is responsible for transporting the positively charged ions. However, polyalanine is electrically conductive. This allows electrons to be transported in the opposite direction. This way, the energy yield can be increased even further. In a mixed membrane, though, the different channels get in each other's way a bit. If the channels are decoupled through layering, the flow through the membrane increases, and that means more electricity for us. The good thing is that the membrane still has a long service life. In experiments, the team has already made good progress. After 16 days of continuous operation, the new membrane still managed over 90% of its original performance. Overall, the research group's approach seems quite promising, but it's still in the experimental stage, so there's a long way to go before a finished plant. But the team at Switch Energy is already further along. They already built the first real osmosis power plant, with some pretty big ambitions. The French startup Switch Energy expects this power plant to generate up to 500 megawatts of electricity in the long run. That would be enough to meet the electricity needs of about 2 million people, more than the population of Hamburg, or Hamburg, how we call it in Germany. So that would be pretty amazing. The power plant is also said to have an energy density of 20 to 30 watts per square meter. To make this possible, the startup uses anode technology. With this technology, Switch Energy is able to manufacture particularly efficient membranes. These membranes appear to enable such a high energy density. Exactly what makes the Switch Energy membrane so special is of course part of the company's secret, but here's what I was able to find out. So the electrical current is generated through selective transport across a membrane. This membrane consists largely of cellulose, and there are also a huge number of nanochannels within the membrane. The secret behind the Switch Energy likely lies in a special titanium oxide compound. This is located on the outer wall of the nanochannels. This appears to result in a particularly high ionic current. This is how Switch Energy managed to achieve such high efficiency. This is a basis for the new power plant that has just been finished. Interestingly, I follow the project for a while now, and in the beginning I found it under the name Osmoron 1, and now it's called Opus 1. It is set up at the Rhone River in France. And in the next 10 years, additional plants are planned to be added, so the project is expected to reach a total capacity of 500 megawatts. Many investors agree that this sounds quite promising. The company recently raised another 25 million euros for the project, and Switch Energy was also represented at the European Inventor Award, a prestigious award from the European Patent Office for inventors, and I was honored to host this event 2 years ago, what was really exciting for me. So the next big step for the company is actually to pave the way for mass production. And all of this sounds pretty good, and there really does seem to be progress on this front. But as always, I have a little something to say about it in the big hurdle, the part in my videos where we also look at the critical points and limitations of a technology, just like you would do in a scientific paper. And like in every scientific work, I also always quote my sources. You find the numbers down here and then the links to the sources in the video description. Okay, let's start with the big hurdle. To begin with, we should start looking at the research from the university before we move on to the startup. As for the research group's new membrane, it seems quite promising, but so far the yield is still pretty low. Using a test system, they were barely able to power a wristwatch. Currently, scalability seems to be one of the biggest challenges. Developing and producing such a membrane requires very expensive, precise instruments. This could also make it difficult to produce the membranes in large quantities and on a large scale. But to be clear here, this is often the case with things being produced in university laboratories, so maybe when scaling it up, this can get way cheaper. But at the moment, the same applies to Switch Energy. While the whole concept seems quite promising, the electricity remains relatively expensive for now. According to the EPO, the cost per kilowatt hour is currently still 15 to 18 cents, making it slightly more expensive than nuclear power, which ranges from 13.1 to 20.4 cents per kilowatt hour. In the long term, however, the price is expected to drop to 5 to 8 cents. Compared to solar and wind, the price of the Osmosis power plant is still twice as high. But that said, I would argue that osmosis power plants are particularly interesting for baseload, so this hurdle doesn't carry as much weight for me. More importantly, the construction of many osmosis power plants could lead to further problems. The power plant could cause local drops in salinity, since fresh and salt water no longer mix as they used to in natural estuary. In addition, the discharge of brackish water causes temperature changes. This could alter the local ecosystem. All these risks are currently very difficult to assess, as there aren't yet many large-scale projects. At least as things stand now, while there may be local impacts, the quality of the water remains unchanged. That's why I would currently rate the overall impact as medium to small, and I think the technology is very exciting for the future. So the big hurdle today is actually just a small hurdle. But what do you think? Please write your opinion in the comments, and thank you for all the interaction under my videos, and a special thank you to the viewer who sent me my very first community letter from the US to Germany. I was really excited to get this letter. It contains a paper that I'm currently researching about and hopefully can make a video about it soon. And with that, vielen Dank fürs Zuschauen, which means thank you for watching. Auf Wiedersehen, your Jacob.